This experiment, we will be considering galvanic cells that can be made from the same redox reaction on both half cells, but as a function of differing concentrations. And so just a little bit of review in case you haven't quite reached this point in the discussion in lecture. There are two components of a redox reaction. You have your reducing agent, which is going to be represented here by R, and you have your oxidizing agent. So the reducing agent gives electrons to the oxidizing agent. Another way we can think about it is the oxidizing agent takes electrons from the reducing agent. So after the reaction, whatever was your reducing agent is now more positive because it lost electrons, and whatever is your oxidizing agent is now more negatively charged because it gained electrons. And in whatever the balanced reaction is of this reaction, we would have n number of electrons transferred, and that value is important in some of the calculations regarding galvanic cells. So if we were to look at the setup of a galvanic cell, essentially what we're doing is taking the redox reaction and separating out the two half reactions. So we have the half reaction of R becoming Rn plus, and we have the half reaction of O becoming On minus. So we usually will draw the reducing agent on the left side. So we have R becoming Rn plus, and so I'm going to draw that in my left half of my cell, and O becoming On minus on my right half of my cell. If we think about what is actually going on here, the reducing agent is the one losing electrons and the oxidizing agent is the one gaining electrons. So the overall flow of electrons would be from left to right in this cell setup. And that is actually detectable by a voltage. And so in this case, you guys will be using multimeters in the lab to measure the voltage between two half cells. And in order for that to actually occur, you have to have a salt bridge. And so this other line going back the other direction is to represent our salt bridge, where we have an electrolyte that can flow in each direction to allow the overall flow of charge, and we don't get like a huge charge buildup on one side or the other. So positive ions will go towards the right cell because we're getting a buildup of more negative stuff, and negative ions will flow towards the left side, so because we're getting a buildup of positive things, that allows the overall charge balance in either solution to be more neutral over time, and the voltage can continue as electrons are flowing. So this is typically done in a galvanic cell where R and O are different metals, for example. But in a concentration cell, R and O would be the same metal. The only difference is the concentration. And so in this lab, we will have copper metal. Actually, let me write it below because it's going to take up some space. All right, so copper metal becoming copper 2 plus on the left cell. And on the right cell, we'll have copper 2 plus becoming copper metal. And so to have this happen, you have to have your solid metal electrode in the solution. So I'll draw that. And the solution has your copper 2 plus at some concentration. So I'm going to set this left half to be one concentration and the right half to be some other concentration. Now, I'm going to draw a lot more dots in the right half, and that is because there should be a concentration differential between the two. Okay, so if you think about it, we have copper metal turning into copper 2+ on the left side and copper 2+ becoming copper metal on the right side. The kind of driving force here you will be thinking about in this experiment, so I don't want to give too much away, but hopefully this visual can help you at least get started on that thought path as to why I drew the right side as having a higher concentration. You can think about what direction the electrons would flow based on how we've labeled this as well. All right, so the overall reaction of our redox process with the two half cells has some delta G value associated with it, Gibbs free energy, and that is usually thought of in terms of a per mole basis. And we can also think of the standard Gibbs free energy in terms of standard electrical cell potential. So usually you'll see this with the little circle representing per mole for the Gibbs free energy, and you'll usually see the standard electrical cell potential, which would also have a little circle to represent per mole. But we can also write it this way, where it's not on a per mole basis, it's a non-standard cell potential and a non-standard delta G value, times the number of electrons transferred, times Faraday's constant. Another equation that we may have seen before using delta G to compare the non-standard value of delta G to the standard value is that delta G is equal to delta G naught plus RT ln K. And R is, again, our gas constant in joules per mole K. T is our temperature in Kelvin. And then ln of K is the natural log of the equilibrium constant for the reaction. Just remember, these are reversible reactions. One direction may be more favored than the other, but we will have a K value associated with it. So we can take this form that compares the non-standard to the standard version and plug in each version of the relationship between Gibbs free energy and the electrical cell potential and get what we call the Nernst equation, which compares the non-standard cell potential to the standard cell potential with this extra term added on. And so that is, again, gas constant, temperature, number of electrons, Faraday's constant. And now, instead of writing it as ln of K, we're going to write it as ln of Q because we are at a non-equilibrium state most often. And in the case of, if the reaction was at equilibrium, we wouldn't really see a voltage anymore. So Q is to represent that not being at equilibrium. So what is the ratio of the actual concentrations in real time? Okay. So the setup for this experiment is that you will have some different weigh boats, and they'll be arranged around a central electrolyte solution. So that electrolyte solution has the positive and negative ions that are needed to form your salt bridge. And so we'll use filter paper to make a little bridge between the center solution and whichever two solutions we're actually trying to measure the voltage between. And you are going to look at a range of concentrations of copper 2+ as the experimental variable here. So the concentration of copper 2+ is our variable, and this one is 1.0 molar. And for example, this one is 0.1 molar. And as we move around, the concentration will continue to decrease. Oh wait, I said 0.1, not 0.01. So as we move to this one, it would become 0.01, etc. So we will continually compare the voltage to the initial stock solution at 1 molar with each of these differentials in concentration, and we'll just move our salt bridges and put electrodes in whichever solutions we want to measure voltages across. So, in thinking about the fact that we have the same reversed version of the oxidation reaction and the reduction reaction going on in our two half cells, you would quickly realize if you were to look up the standard cell potential that you're going to get the same value for both of these. It's just the negative of this value. And so that would give you a E cell standard, or the standard E cell value would be 0, because you're comparing apples to apples here, copper reduction to copper oxidation. The only term that can actually allow us to have an actual measured voltage in this concentration cell setup is going to come from this term here. And because we're specifically looking at concentration, we're looking at differences in the value of Q in our setup. You could also set up another reaction or another set of cells that would vary in temperature, and that could also get you to have a positive E cell value. But we're focusing on varying mainly just the concentration. And so the rest of the equation, you will use that in thinking about and modeling what is going on and reasoning with the data that you obtain for this experiment. And so we have, as I mentioned, our two half cells, copper metal becoming copper 2+ and copper 2+ becoming copper metal. So we want to know if we let one of these be at a higher concentration and one of these be at a lower concentration, what would the voltage of the cell be in our two half cells separated from one another.